Good morning, all. Let's recall what we are doing in last class. So, given an element of H star, we have constructed a Verma module. We denoted by m lambda. Verma module is an highest weight module. And not only that, to be highest weight, the minimum relations are needed. Only those relations are given in this m lambda. Only those relations are there in m lambda. So in other words, there is a surjection between m lambda to any highest weight module, because any highest weight module need those minimum relations which are there in m lambda, and also there could be many more. Okay, and we also said it has every highest weight module has a unique maximal submodule. So you quotient by that unique maximal submodule. What you get is, by definition, it is an irreducible representation of G. This is infinite dimensional, possibly, and we proved that it is in fact finite dimensional in some cases. So if and only if, so it is only finite dimensional when lambda belongs to dominant integral weight. So this is by definition lambda of hi is non-negative integer for all I. L is the rank of G. Okay, so if this happens, then the vector, so namely Fi, this lambda of hi plus 1 acting on this V lambda. So V lambda is the generator for m lambda. And this will be another highest weight vector. Another highest weight vector in m lambda. That's we proved it. So it generated by this highest weight vector will be a submodule of m lambda, which is also this is a highest weight module now. So n plus kills it, this vector, and h is fixes this, and there is only n minus left. So in n minus, there are no relations exist, because this module is sitting inside m lambda. So m lambda has no relations involving f. So this module also should not have any relations involving f's. So this is another Verma module whose weight is same thing as the weight of this. So the weight of this, so highest weight vector with highest weight. So this dot action we have defined. So whatever this vector we're seeing here, this weight is Si dot lambda. So if you remember that the definition is Si of lambda plus rho minus rho. The rho is the sum of the fundamental weights. Okay, so this Si dot lambda will sit inside m lambda. Okay, so this is one copy of a submodule. So for each this happens for each I. So m lambda has many submodules. You quotient by them. So m s1 dot lambda, m s2 dot lambda, m sl dot lambda. And the claim is this is a maximal submodule of m lambda. you are in this setting, when lambda is the integral dominant integral weight, then this is a maximal submodule. So that means that this is same thing as V lambda. So this is, so how did we prove this? So this is, it's enough to show that this is finite dimensional because this is the highest weight module. If I also show it is finite dimensional, it will be irreducible. So this should be maximal submodule. Okay, so to show this is finite dimensional, we need to know about these weights. So what we proved here is, or at least give an idea, the weight spaces of this module, and that is V lambda I'm denoting. Weight spaces are Weil group invariant. So to show this, it's enough to prove for, instead of proving for all Weil group elements, enough to prove for some SI, which is a generator of Weil group. Once this is SI, then there is an automorphism we told, which involves exponential of EI action and FI action. And those actions, if you want to define exponential of those actions, you should know that on this module, they act nilpotently. Then only exponential definition makes sense. So to show this on this module, they act nilpotently. For example, if you take EI, because there is a maximum cap for weight, so on this module, after hitting many EAs, every vector after hitting many VAs, it should not cross lambda. So that's at some stage it kills. So EA acting is okay. FI acting, we said that so MSI you're quotienting by this means in this module this FI is killing. So this is 0. So you're quotienting by this module. So this is 0 in this. So the conclusion is Fi acting on the generator nilpotently. Once Fi acts nilpotently on a generator, the typical elements here looks like, even in the M lambda, it looks like some bunch of Fs, some powers. And on such elements also Fi acts nilpotently because the root string length is at most 4. Right? So that's a thing at the end I wanted to convey. So because you can't have root strings, so for example, you will be in some situation like Fi, and then there will be some F alpha. So this is like alpha plus 3i kind of a, that will lie in alpha plus 3i. So that root string, when you go, this should not, maximum 3, maximum 4. So if you hit one more time, so this is already alpha plus 3i is there already. So 4 are there. So you can't, one more time it will be 0. So something like that. So that's the argument which tell you that the automorphism which involves exponential can be used on this module. And once if it is well defined, then it's very easy calculation that the weights of mu under that automorphism map to SI mu. So that's the idea of the proof in showing this, okay, using the automorphisms involving exponential. And once you have this, what is the conclusion you are getting now? What are the weights you are getting now? So weights of V lambda, I mean actually this, weights of this are actually Weil group invariant. So they are Weil group invariant. On some mu's, I don't know. So they are in H star at present. And what the information I know that weight is always less than or equal to lambda. Okay. So if you see this, this condition mu is less than or equals to lambda. Okay, if you analyze what is mu is less than or equals to lambda, means lambda minus mu can be written as some positive integer linear combination of simple roots. So this tells you that if you evaluate on HIs, so the conclusion here is so mu is the weight is actually lambda minus this, and this one, if you act on every HI, what you know that this is like alpha I check, and this alpha j and alpha I check is an integer that is because they form a root system. Okay, so we have not seen a proof of this, but I mean, if you use a killing form, means this is actually involved in the statement that this alpha is from a root system. So this is an integer. Alpha is acting on this is an integer, and lambda is anyway dominant integral weight. It's a non-negative integer. So finally, what you are getting is this mu acting on HIs. You are getting integers, maybe negative, maybe anything. So, but this is a very nice property, very nice restriction of the weights. So this tells you that mu lies in the weight lattice. So this lambda, I'm not denoting by plus now. So this is by definition, it's a integer combination of fundamental weights. Okay, so because this is an integer and omega is a dual to this, so this is exactly what you are now. So mu's are lies in weight lattice. So what is the conclusion now? So the weights of V lambda, they are while group conjugate of mu belongs to now only the weight lattice. Mu less than or equals to lambda, still there. Now, weight lattice means what now? It's an integer linear combination of this. So W, what it will do, it actually moves, right? So moves everything to fundamental chamber. I mean fundamental chamber, I mean even including walls. So I'm also including the walls. So it's a fundamental chamber closure, right? So this is where the dominant integral weight, even including the closure, this is where the dominant, so here omega 1, omega 2 are there, if you remember, and it's integer linear combination we have seen here. This is the lambda plus. Lambda means some integer here, maybe mu is here. But once you act with while group, the mu will be taken into a dominant integral weight by a while group. So the conclusion now is you can replace, in fact, some dominant integral weight. Okay. W you keep it. So the orbit of any mu has a one dominant integral weight, and so you can take the mu is to be dominant integral weight. So now it is easy to see that this is a finite set. So this is a finite set because under some lambda, let's say somewhere here lambda is there. Under it, there are only finitely many dominant integral weights in this fundamental chamber. Okay, so this is a finite set. Weights are finite, so this is a finite set. Once this is a finite set, and I know already each weight space is finite dimensional, so my conclusion is this is a finite dimensional. So these weights are W invariant, and weights are in the integral lattice, and so that weights are while group orbit of only in the dominant integral weights, which are less than or equals to lambda, but those are only finitely many. And each weight space is finite dimensional even in this space because some span of Fi's are there. So in this space also. Okay, so this is a proof to show that why this is finite dimensional. Then it will be automatically equal to the It's irreducible, so it's equals to V lambda. Being okay. So now this useful property here you are seeing will make you that this you are allowed to define now. You can define what is called character. Okay, character of any representation. In particular, this V lambda. So it's this definition makes sense for any representation. So what is the definition? It is only collecting all the weights, and then what are the weights? So it is only collecting e power mu, which is mu is a weight and its dimension, and mu is at present in H star. But if you take V lambda, then mu is less than or equals to lambda, and this where is this element is belongs? It is in the group ring of lambda weight lattice. So this weight lattice is actually spanned by mu's. Mu's are there. So, but I'm taking as a e power mu as a notation. So I'm thinking this lambda as a multiplicative group. So this has a basis with so this is this set. Yeah. So I'm thinking as a multiple group. So instead adding mu plus, that's good enough. So if you think this lambda as a multiplicative group, e power mu is there in lambda, and this is an integer linear combination of e power mu. So this entire thing will be there in this. So it's a finite sum. Because it is actually, you can now replace with what do you know? Yeah, please.
Can you please explain what e power mu is?
E power mu is a symbol. So actually lambda to another lambda, it's the same lambda. So this is the addition here. A group is, there's a mu here, lambda is here. Okay, it's a weight lattice. I'm actually converting into a multiplicative group by defining it to be e power mu. It's the symbol again. So it's a group homomorphism.
Okay.
So it's just a symbol which actually collecting only the mu's. So it's only capturing the mu's information, what weights are coming and what is the dimension of the weight space. That's all it is capturing. And you know that it comes means W invariant. So this makes you e power W mu I am writing for every W in capital W. This is a while group. All these weights, so you're seeing all these weights should have the same dimension as muth weight. So the coefficient must be dimension of V mu itself. Okay, so it's supposed to be VW mu for each W mu, it's supposed to be VW mu. But because they're all are same, I took out, and each WR bit has a dominant weight. So you can assume that the mu is in the dominant weight, and mu is less than or equals to lambda. Okay. And this is now, so now what is this belongs? By the fact that it is W invariant, the symbol for W. So it's a W invariant elements in this group ring. That is where character belongs. Okay. So if you, I'll explain in an example what is happening here. So this is same thing as if you took out lambda out. So let's say it is less than or equals to lambda. So every representation has the lambda as a one weight, definitely. Now what we proved that, what is the dimension? So how many times the highest weight vector exists? It's only scalar multiple. So what are all the highest weights? It's only scalar multiples of V lambda. So it's a one dimensional. So if you separate lambda out, what you are getting is it's a e power W lambda, where W is in everything. So this is also telling you that every weight space, not only lambda the weight space, because we proved that any wild orbit of that also should have the same weight space. The weight spaces are, the dimensions are equal. So dimension of this is also 1. Now the remaining is mu less than lambda but not equal, and mu is a dominant weight. The same thing I am writing. I don't know. There are many dominant weights below it. Below it, many dominant weights are there, but I don't know their dimension yet. So my goal is to tell you how can you get these dimensions, okay? And also, what else? So this is a character. This is a symmetric polynomial. So I have to give an example before going. So do I need to tell anything here? Okay, so let's go to an example. Even in the SL2, my lambda is now the dominant integral weight is n. N is actually, it's not an element of H star. It is an eigenvalue. What is n? It's an eigenvalue on the highest weight vector Vn is nVn. Right? So this is a HVn is nVn. That's only one vector we took it. But if you want to write H star, I have to know what are all the diagonal entries where they are mapping to. So it's only d multiplication happened both sides. So dn. So if you want to write as an element of H star, what is that element you have to look for? This matrix is mapping to some scalar dn, and that is same thing as n times the projection. So the first projection, right? So this is if you want to think as okay, this is the lambda, and now what is a character? So Vn, you already know what Vn is. It's a spanned by, in fact, it has a basis with small Vn, f dot Vn, f square dot Vn. At the end, you can go to Fn. So this has a basis by this, it's a species. So if you write down the weights, this weight contributes, I want to write down the character of Vn. By definition, it's a sum of all over all the weights. I have to write what is the weight of this. So it's a n epsilon. So I have to write e power n epsilon. And with what dimensional? It's only one dimensional. And this weight is n epsilon 1. When you act with f, you have to subtract with alpha. That is alpha 1, f alpha 1. So the alpha 1 here is epsilon 1 minus epsilon 2. That's the only root. So you have to subtract this. When you subtract it, so the next coefficient you're getting is e power n minus 1 epsilon 1 plus epsilon 2. Then keep going. What is this last weight? It is n epsilon 1 is the Vn. And your f times applying, so that is same thing as it should be minus n actually. So the minus n is n times alpha 1, I am telling, n times, which is same thing as n epsilon 2, which is same thing as minus n epsilon 1, right? So you need to get a minus n there. n2 minus n it goes. So this is e power n epsilon 2. And every weight space is one dimensional. What we are actually doing, so far what I told, there is a, in each weights, weight, whatever weight you have, for example, this, you act with W. When you act with W here, so the while group here is S2, it only swaps epsilon 1 to epsilon 2. So if you act while group here, it should go to n epsilon weight, under by the while group element, which is swapping this transposition 1, 2. So these two weights have the same weight space. And what we told again, there is something less than or equals. So what are the weights? So we have seen the description of the weights. You look for all the dominant weights. and which are less than or equal. It's while group conjugates. It's while group orbit. So I have drawn the dominant weight. First dominant weight, they are one dimensional, and the second dominant weight. So this one, if you check it is dominant or not, so you have to evaluate on H1. So it's n minus 1 epsilon 1 plus epsilon 2. If you evaluate on H1, what you are getting is n minus 1. So it is n minus 1 epsilon 1 plus epsilon 2, right? Correct, yeah. So this is greater than or equal to 0 only if n is bigger than or equals to 1. So if n is 1, only these two elements will be there because the dimension is 2, 1 and minus 1. If n is bigger than or equal to 1, there is another dominant weight will be there, and its negative will be here somewhere, this next to this. So what you are doing now, you are taking all the dominant weights and you are taking all while group orbits of that. And the beauty is, whatever dominant weight you take it, for example, n epsilon is the dominant weight, its while group orbit, the numbers are same, the dimensions are same. Here you are not seeing the, this dimension may actually change, but here you are getting same dimension. So, okay, anyways. So let's understand this sign. What is this is telling? If you want to see like a polynomial, so this is actually S2 invariant polynomial, right? W to S2 means if you swap 1 and 2, it remains same. So that's what is the W invariant polynomial means. So if you want to see, actually substitute e power epsilon 1 as x1. If you really want to see as a polynomials, epsilon 2 as x2, and what the polynomial you're going to get is x1 power n. Here x1 power n minus 1 x2, and at the end you are getting x2 power n. So this is a symmetric polynomial of degree n. Okay, and this symmetric polynomial, so that's what you are going to. So this whatever this notation I am telling, this this notation, if you want to see in terms of SLNC, they're all symmetric polynomials in n variables. So just if Z notation, this is a polynomial ring. By replacing e power epsilon 1 as x1, this is identification. What do you get is all symmetric polynomials. So the characters of V lambda in terms of SLN, it's exactly the symmetric polynomials in n variables. If you want another type, you not the SLN, other types, it is a while group invariant. The while group may not be Sn there, so that's why it is only while group invariant. Means that is also a symmetric polynomial motion in other types. So if it's, yeah, so these polynomials are well known. So these are the symmetric polynomials, and this polynomial, one way to write it is so this is I can write in the determinant form, namely x1 power n plus 1, x2 power n plus 1, 1, 1, and determinant is actually not a symmetric polynomial, it's alternating polynomial. So you divide by one more alternating polynomial, you get a symmetric polynomial. Alternating means sign changes if you swap the x1 and x2. Okay, and these two are same. It's easy to see. What you are saying here is you just multiply x1 minus x2 to this. What you get is this minus this. It's easy calculation to see that these two are same. But I wrote it in this way mainly because I know this this is exactly same thing as what is the determinant formula? It is actually some while group will come, some sign of the permutation will come. Determinant, A1 sigma 1. So A1 sigma 1. So A1 sigma 1 and A2 sigma 2. So A2 is 0 here. So that is a determinant formula. And by this is same thing, x sigma 1 power 1 itself. Okay. And what you are seeing here, even if you further convert into, if you want to replace x1 with further resubstitute with e power epsilon 1. So what do you get is sigma x2 minus 1 power sigma. X1 is e power epsilon 1, so e power epsilon of sigma 1. E power epsilon of sigma, so n plus 1 is there, right? So what is it happening? X1 power, so there is n plus 1 is here. If you replace x1 as e power epsilon 1 and x2 as e power epsilon 2, e power n plus 1 times epsilon sigma 1, here only sigma 1. Now, why I'm writing this? So this formula is well known, formula which gives a character of any irreducible representation, namely the Weil character formula. Whatever you are writing here, this way. So this is exactly the Weil character formula. Maybe you have to replace this. What is the meaning of? So this is the same thing as minus 1 power sigma. How sigma acts on n plus 1 times epsilon 1 is same thing as it swaps 1. So this sigma 1, it is same thing as sigma acting on that epsilon 1. So once you write this, so this is exactly sigma of epsilon 1 now. And this formula, this is exactly the Weil character formula, which gives you the character of irreducible representation for any dominant integral weights for any type. This is sigma belongs to Weil group element minus 1 power sigma. For Weil group element, what is the minus 1 power sigma? So it is not a minus 1 power sigma. It is a sign of sigma, which is actually length of sigma, length of a permutation. So you know a length of a Weil group element in general, but otherwise also whether it's even or odd permutation. So the length is like, product of simple. How many times you are writing as a product of simple transposition? So, okay. So it is a sign of a permutation. That's it. So it's the determinant definition, right? So I'm using just a determinant definition here. Okay. So e power sigma. This is the length of W, length of sigma. Sigma, what is this? N epsilon 1 is my given lambda. So lambda should be there. What is that epsilon 1 there? That's exactly the rho, which which yesterday we have seen. Rho is actually the sum of the fundamental weights. So that rho will come. So rho in SL2 situation, it is the sum of the fundamental weights. So it's only omega 1, which is same thing as epsilon 1. That's why in SL2. That's why you are not seeing there. So that by e power sigma rho. Okay. So this is exactly the formula you are seeing. So whatever you did, you verified in this SL2 theory, right? And that is actually more generally true due to Weil. Okay? This is a Weil character. It gives a character, but unfortunately, this is alternating sum, and so it doesn't give you. See, what is interested for me? I want to know character
I have a
means.
question.
Sorry, please.
Yeah, what is the length of an element in the Weil group?
When you see Weil group is generated by product of simple reflections, right? So Weil group, for example,
Yes.
in S3, every permutation can be written as product of consecutive transpositions, right?
Yes.
So there are the simple reflections. So length of a sigma. So this is the Weil group. Length of a sigma means when you express sigma in terms of product of transpositions, right? So for example, 1, 2, 3, I take it. I'm writing as you have to write in the product of this. So maybe I don't know. So this 1, 3, 1, 2, I think, right? So then this 1, 3 can be written as so 1, 3 is what? 1, yeah, in terms of 2, maybe it's a conjugation. So 1, 2, 1, 3. No, I have to change 3 to 2. So 2, 3 is here. 1, 2. So this is no, what is happening here? So anyway, so maybe I'm no, the definition I'm telling. So I'll erase because I'm not writing correctly. I don't want a 3 there. So you are able to, you can express this element as a product of these elements in many ways, but you take the least expansion, least length expansion, you count how many are there. So when you take a W, you express as a simple reflections. So it will be SI1, SI2, SIK. When you express it, there are many ways you can express. And you take the least expression of it, and how many times are there, it is the length. That's one way to do it. That is a minimum length expression when you express a while group as a product of simple reflections. This is the minimum. K is minimum such that sigma can be written as like this. That's the length.
So, I mean, is there any longest element or something like that inside the?
It is, yeah, it is there. So if you, there is also a length, maybe, so length definition is also which takes all positive roots. So length is exactly number of positive roots which maps to negative under W. So this is the easiest way to, well, this is one more way to tell is number of positive roots. When you apply W, it goes to negative. Okay. So in SL3, S3, all the positive roots are epsilon1 minus epsilon2, epsilon2 minus epsilon3, epsilon1 minus epsilon3. If you want everything go to negative, so you need a permutation which takes 1 to, so maybe you reverse it. So instead this way, so 1 goes to 3, 2 goes to 2, 3 goes, so I'm reversing. When you're reversing this, so this is a while, this is the longest element because it changes everything to its negative roots. Is that's okay?
So the longest element is the one which takes it to its negative.
Which sends all the positive roots to
positive roots?
negatives.
Oh.
And one more way.
Can we express it in terms of S alpha is a simple? I mean, the reflections corresponding to the simple roots.
In SL5, the while group is S5. So the reflections are like consecutive. S1 is 1, 2. This is while group is generated by 1, 2, the consecutive. So this is S1, S2, S3, and S4 is 4, 5. So the group generated by this, and longest element can be written as, maybe in S3 I'm going to write. So longest element is what it is. It is 1, 3. Okay. So in general, in S5, what is the longest element? It is the same thing. It reverses the order. So 5, 4, 3, 2, 1. So it changes all the positive roots to negative. And when you express in terms of product of simple roots, for example, if I write here, this length is S1, S2, S1. Means the 1, 3 can be written as 1, 2, 2, 3, 1, 2. So this is a conjugation. So only 2 should change to 1, so that you get that, right? So this longest element you are able to express as product of simple roots. And how many simples are there? There are 3 many, and this is a minimum length expression. So that's why this length is 3, because you are expressing minimally like this, or this changes all these positive roots to negatives. So that's why length is 3. There are 2 definitions. Is it okay?
Yes, yes, thank you.
Okay, so but the problem with this is this character doesn't give me directly what the dimension is, because the formula is not nice. So I want the dimension of I want this. This is very useful information. Weight space dimensions I'm not getting here. So that's why there are many other also known. So maybe I will. So I need this space, because so this thing I also can be written. So I'm going to there are some other methods which are known how to get directly a dimension of V lambda mu. This character is not unless you expand it into in terms of this, you can't write it. So the other ways is whenever n epsilon 1 is there, right? So this is n epsilon 1. So there is a partition. This is my lambda. This partition has a Young diagram, which is there are n boxes. Okay? And how do you get this term? This term you get it by you're filling all the boxes with 2. So if you fill all the boxes with 2, so you're basically, so these are called semi-standard Young tableaus. What is a semi-standard Young tableau of given partition? The partition you arrange in a Young diagram and fill the diagram with ones and twos in S2. Here ones and twos you are allowed to fill such a way that, so for example, if I want next one, the next one is x2 power n minus 1 x1. So I have to fill 2 n minus 1s and 1 n minus 1 ones. So the rule of semi-standard Young tableau is 1 should come first and 2 everywhere. So it's a weekly, in this direction, it's a weekly increasing. So you can fill, how many ways you can fill this tableau. So this n size with ones and twos, and that's it. That gives the dimension. If you want a weight space, for example, this weight is exactly the number of twos. So x2 will come number of twos. So the weight of any tableau. So any tableau looks like this. Any tableau in this situation, there are a bunch of ones and bunch of twos. Weekly increasing, it should be like this. And weight of this is given by x1 power number of ones and x2 power number of twos. So in other words, all these things you are seeing here, these terms. So for each of them, there is a unique semi-standard tableau whose weight is this. Right? So there's a weight of a tableau which is given by this number of ones, right? So similarly, if x1 power n is there, you have to fill with all the ones, right? So for each of them here, you can fill it. So this filling business, so this is very useful in giving a character of Young tableau. So character of a means this is very special about SL and C. I'm only talking SL and C. I'm telling you that character of V lambda, you can get it by so lambda is a dominant integral weight, but when you express in terms of epsilon ones, yesterday we have seen that it gives a partition. So this is lambda i's are actually non-negative integers. I get a partition because when you express, so this is actually equals to, if you can check this, this is equal to lambda 1 epsilon 1 plus lambda 2 epsilon 2 plus. Because omega 1 is epsilon 1, omega 2 is epsilon 1 plus epsilon 2, something. So we did this in the tutorial yesterday. So given a partition, there is a semi-standard Young tableau. And this is the lambda 1 boxes, lambda 2 boxes, lambda 3 boxes. You're allowed to fill this tableau with ones and n's. So fill 1 to n. Such a way that weekly increasing along rows. This way weekly increasing, this way strictly increasing. So for example, a tableau looks like 1. So 1 should come in the only first row, for example. So strictly decreasing means 2 should come, 2 can be here also. But 2 can't be here in the third place because above you can't put anything 1 and so you are forced to put, it's strictly decreasing. So you have to put here something above it, something 2. It has to be 1, but there is nothing left to keep it here. So the thing is, number of ones comes in the only in the first row. So this number of ones is a mu1. Number of ones and twos, this is mu1 plus mu2, which is comes in the first and second rows. And eventually you have to fill every box with all the 1 to n's. And that means the sum should be equal to this. And whatever this you are definitely, this is exactly same thing as whatever notation for you is mu less than or equal to lambda. So you are writing, right? Mu less than or equal to lambda means what? Mu lambda minus mu. You are writing as a positive linear combination of k1 epsilon 1 plus k2 epsilon 2, where k's are non-negative integers. And if you analyze this definition, you write in terms of epsilon i's. So mu is mu1 epsilon 1 plus mu2 epsilon. So lambda is what? In SL3, lambda 1 epsilon 1, lambda 2 epsilon 2 plus 0. So that is a, because the last coordinate should be 0 in when you want a dominant. So anyway, so you write in terms of epsilon i's and see what you are getting here is, so for example, what is this lambda minus mu? Okay, that's exactly telling you that lambda 1 minus mu1, first epsilon 1 coefficient. Here, what is the epsilon 1 coefficient here? Epsilon 1 is only coming here, it's a k1. So lambda 1 minus mu1 is greater than or equal to 0. What is the epsilon 2 coefficient here? It's epsilon 1 minus epsilon 2. It is epsilon 2 minus epsilon 3. So k2 minus k1. Here epsilon 2 minus epsilon. So what is that you are getting? So maybe mu1 is equals to k1. No, sorry, lambda 1 minus mu1 is k1. Lambda 2 minus mu2 is k2 minus k1. If you add them, you get a k2 which is a positive. So if you add them, this should be positive. That's exactly this. So anyways, so the existence of semi-standard Young tableau is guaranteed corresponding to each weight. And you collect all the semi-standard Young tableaus, you sum it over that. So x1 power number of ones, x2 power number of twos, xn power number of n's over any tableau, semi-standard Young tableau, that gives a character of v lambda, which is very useful in a SLN situation. That gives you actually the weight space dimension. How do you get the weight space dimension? You have to fix mu1 now. And what is fixed mu1 means? X1 1 should come mu1 times, 2 should come mu2 times, n should come mun times. So you're looking all the tableaus from where 1 mu1 times 2 all the semi-standard Young tableaus. So that number is counted by k mu lambda, which is a Koska number. So this is a Koska number, which is very well known in symmetric polynomials. And so this counts number of semi-standard Young tableaus of shape lambda and weight mu. So that means, yeah, so then you are varying over all the mu's, all the weights. So for example, if you want a lambda tableau, the tableau corresponding to lambda 1, the weight is lambda 1. If I want weight is lambda 1, lambda 2, lambda 3, lambda 4, that means number of ones has to be 1, lambda 1. So ones have to be filled here, right? So means I'm telling that weight lambda tableau is unique. Weight lambda tableau is, weight lambda means lambda 1 should be there. That's the only way you can put it. Lambda 2 is only this way. Lambda 3 should be equals to mu 3. Number of 3 should be lambda 3. So that is exactly telling you that the weight space of lambda weight space is one dimensional. Okay, so this is all. There is something more concrete models are known for to define a character of V lambda. So finally, what you are getting here is dimension you are getting in SLL is the number of semi-standard Young tableaus of shape lambda. So dimension of an irreducible representation is you take all the semi-standard Young tableaus of shape lambda and you fill the mu ones and n's by taking the count of the ones and twos, you get the weights plus dimension as well. If you don't count them, if you take all, then you get the entire dimension. Okay, I think from after this, there are some known models for character. That's what I want to convey. Okay, so why these characters are important? So the question now is why these characters are important. See, what is a character as what is a character definition? It is just collecting some numbers, right? Some weight space dimension and some weights. That's it, right? It is not telling anything about the representation. It's only collecting the weight space dimension and weight. But the fact is, the observation or the proposition is character determines the representation. Character determines the representation. Okay. What does this mean? I don't know the representation. I don't know what V is. This is a finite dimensional representation of G. I don't know what this is. Someone told me what is its character. Then I can tell them what is the representation. So character V implies, given character V implies, I can tell you we get V. So these numbers are good enough to get back entire V. That's a beautiful object. That's the meaning of character determines the representation. Just knowing the character is good enough to get the representation back. What is the idea? So this is very interesting. No? Only giving a character is good enough to get a V. So someone given me just a character, right? So this is, then what is the meaning of character? It is a symmetric polynomial. So it has some weights and you are collecting all the W mu's over all the while group. And this is a symmetric polynomial. That's it's invariant. So C mu's. So mu is any weight. Okay. So some character is given. Character looks like this. So character looks like it's an integer linear combination of some while group invariant things. So this is the while group invariant. This can be any integer. But in fact, a positive integer, non-negative integer, if it is a representation. Yeah. So now what you do? How do you get V back? So what is the method? So any orbit is a dominant weight. So you can even assume that there are dominant weights out there. Right. Okay. This is all okay. So now there will be some maximum dominant weight is there. So you try to remove that. So there is suppose lambda is there, maximum dominant weight. And what you can do, you remove the character of V lambda from this. So character of V, now subtract with character of V lambda. What is the character of V lambda? If you remember our earlier thing, see character of V lambda has this form, one thing like this. And this form is also there in the usual character because it's a symmetric polynomial, it will be there. And how many times this is coming here? C mu times. So you subtract C lambda times this. So what happens? This entire term will be gone. The highest weight, one of the highest weights lambda is coming this many times. That is gone. Now it is boiling down to some more lesser dominant weights. And further you subtract it. You get finally, you get something like this. No dominant weights are there less than mu. So there's nothing below. Mu is the fixed dominant weight, and so that dominant weight, mu is a dominant weight. There is no dominant weight below it. That's what you get it. And this is in fact a character of representation V mu. If I recall the V mu weights, it has it has while group orbits of weights and some other dominant weights below it should commit, but there is no dominant weight. So it's just that's called minuscule dominant weight. Means there is no dominant weight below it. So for example, fundamental weights are minuscule dominant weights in SLN. Means there is nothing below the dominant weight itself. Okay. So anyway, so finally you get some character of minuscule ones, and you get you get 0 eventually. You subtracted everything, so you got some decomposition like this, and that is good enough to give the V. Then what will become? So you have a Weil's theorem, Weil complete reducibility here. We should break down to some direct sum of irreducibles, right? And so, but here also character of V you are writing in terms of this, right? So here also this. And so what you're getting, character of V, one side you are getting character of these things, and you are getting some other irreducibles, means some other irreducibles you are getting, but the characters are linearly independent by the fact that there is a highest dominant weight exists. So there's suppose this is the highest one. It's easy to show that they are linearly independent. The coefficient should be 0. So it's injection. So there is a unique way you should be able to express every character as a linear combination of irreducible characters. So that's why this decomposition should match with this decomposition. So using Weil's theorem and this fact that you can keep on subtracting these characters, you get the V back just by after seeing the characters of irreducibles here. Okay. And this is also one more thing what this is telling. In fact, what we are proving here is character of V lambdas, where lambda is dominant, forms a basis, Z basis, for the ring of symmetric polynomials. Symmetric means any Weil group invariant polynomials in terms of this. If you want to rewrite this for an SLN, there are something called Schur polynomials. So characters will be Schur polynomials. So this is whatever definition of here we have seen. This is the definition for Schur polynomials. So this is very important. This is Schur polynomial. So Weil character formula is exactly if you combine with the Weil. So whatever you are seeing here, if you analyze for SLN, you get a Schur polynomial. So Schur polynomial is by definition this. So, okay, so the thing is Schur polynomials forms a Z basis for symmetric polynomial. Okay, and after all this, I think I'll state some open problem. This is something about Schur positivity. This is even conjectured in 2014 by Vaijayanti Fourier and Sagaki. What they said, this is so it's not solved again. So it's a conjecture 10 years ago, not solved. So the question is related to when, let's say, if you have a tensor product, when this is sitting inside another tensor product. Okay, so you take G semi-simple Lie algebra, and they're all dominant weights. So when this is sitting inside the other, so the minimum condition you need is dimension of this should be less than or equal to dimension of this, and that's the only minimum. For that, you will get some conditions on lambdas and mu's, and zeta and eta. There should be some relations, and that with that condition, they are expecting that there is an injection between these as a G modules. What is the meaning of injection? If you write this as a direct sum of irreducibles, irreducible, some V news. If then those all should be here. Those all should be here. Maybe something extra is here exist. Some other V's also may be existing. All the irreducibles here in the left hand side should be there in the right hand side up to isomorphism. If you convert this problem to sure polynomials, even SLN, this is not known. So if you convert to SLNs, so what this is asking is, this is a character of this is actually product of sure polynomials. So what this is telling, right hand side is product of two sure polynomials. Left hand side is another product of two sure polynomials. Then the remaining again a representation, right? So it is a symmetric polynomial. Now it is a symmetric polynomial. I know that this can be written as this can be written as symmetric polynomial. So it's a Z basis. So I know it's in terms of Z's, some other symmetrics, new one. So what is asking here, the new ones, the extra new ones here, right? So they exist. Means what you are asking is, can you express as a positive linear combination of this, right? So if I just subtracted this character minus this character, the remaining should be there, right? So yeah, this is the question mark, and this is a question mark. So this is a sure positivity conjecture, which difference of the product of two sure polynomials can you express as a non-negative integer linear combination of the another sure polynomial. So these two questions are same, and even you know the definitions of sure polynomials. Even you know the Littlewood Richardson rule coefficients here. So here there are coefficients for this how many times V nu occurs. Here also those coefficients are there for this, but the comparing them, whether this coefficient is less than or equal to this coefficient, is very hard because the coefficients have some combinatorial description. So it's hard to solve this problem as it is, but even in the SLN, so they did it only for SL3. So even in the SLN, this is still open. When there are some conditions which are they in fact kept it, so they come from the only dimension count. Okay, so this is I just want to state this because this is a very interesting problem. Okay, so maybe the rest of the talk is try to prove the Weil character formula using Harishchandra theorem. Okay, so this okay, so what is Weil character formula is already given. So the idea of the proof of Weil character formula using the Harishchandra's theorem. The thing is, character of V lambda I want to find, but character of M lambda is easy to write. Right? If you remember, M lambda is a Verma module. So there is actually it's a basis. So it has a basis. This F5 power. So if SL3, so this has a basis. So if you observe this weight here, each so you have to count the weight space dimensions, right? So I need which vector is contributing to which weight. So this is contributing to some I1 alpha 1 minus I2 alpha 2 minus I3 theta is alpha 1 plus alpha 2. Then you have to further this explain. So what you are getting now is so if you want to write a weight, so the weight looks like e power lambda minus some k1 alpha 1 minus k2 alpha 2. So or other words, it's a mu. So let's write a mu. So let's this is a mu is equals to e power mu. I want to write it. How many times e power mu is occurring? It is same thing as how many ways this lambda minus mu is this. right? So lambda minus mu is k1 alpha 1, k2 alpha 2. How many write as a positive linear combination of these all positive roots, right? So what I am telling here, lambda minus mu is exactly equals to I1 alpha 1 plus I2 alpha 2 plus I3 this, right? So character of m lambda has a weight space as our mu, and how many times it is coming. So it is exactly this number is costant partition function for lambda minus mu. This is by definition the number of ways you can writing number of ways interpreting lambda minus mu as a positive integer linear combination of positive roots. Okay, that's what you're seeing here. So lambda minus mu has to be a fixed element. That fixed element, how do you get it? How many I1, I2, I3s are needed? How many ways you can get that fixed elements using this I1, I2, I3s? So that's a, so in other words, I think this is another word to write it is, you product it with 1 minus e power minus alpha, e power minus 2 alpha, where alpha is positive. What this product is doing, this product is doing, it's over all positive roots. Each term it picks one positive root, and another product picks like alpha 1 is there. So this is like alpha 1. This is like something 1 minus e power minus alpha 1 minus 2 alpha 1, and then there is a minus alpha 2. Then this product is minus theta. So writing lambda minus mu as linear combination of this alpha 1, alpha 2, this alpha 1 is same thing as this I1th coefficient come here, I2th coefficient from in this. So e power minus I1 alpha 1 times e power minus I2 alpha 2 times e power minus I3 theta. So the product is exactly telling you how to get this weight, fixed weight. Okay, but there is a negative term is coming. So let's what is this coming? So this is exactly negative of those things. So you are getting negative of those things. You subtract that, so you add them. So e power lambda, if you multiply it, whatever this resulting thing, that should be the character of m lambda. So because this product is giving you how many ways these numbers are possible to get it. So that's exactly the that's a no, how many ways these numbers, right? So there is a lambda is missing there. So you have to multiply with the lambda to get back the weight mu. Okay. So once you have written like this, so this is e power lambda by it's actually the inverse. 1 minus e power minus alpha, it's a 1 minus x inverse is like this. It's a formally it works. You multiply it, you get the 1. Okay. So this after this, so what you got so far? I know m lambda character very easily. So the beauty is you want a character of v lambda, which is difficult to, but character of Verma modulo is very easy, and somehow you get a character of v lambda, okay, with the help of m lambdas. So that's a statement that is you can achieve. So this is where the Harichandra theorem is doing. So maybe observation or proposition. First thing is m lambda. So I'm going to prove that m lambda character I know. I use them to get the character of v lambda. So before that, what I need is this m lambdas as a filtration. So if you try to write a filtration for this could be an irreducible. If it is not irreducible, there is some proper submodule exist. Then if this is irreducible, then you close it. Otherwise, there is another proper submodule exist. Then this, so right. So this is going like this. And here, this process stops in finitely many steps. To stop this filtration of m lambda infinitely many steps in finitely many so what you need is we need Harishchandra theorem. What Harishchandra theorem will tell you. What is this filtration? This filtration is exactly m lambda by such a way that so it's a decreasing. Everywhere is maximal submodules. So m lambda by w1 is irreducible. Let's say the irreducible should be v lambda. The v lambda occurs only once because m lambda has only one highest weight vector. So the successive quotients are irreducible. So w1, w2 is another irreducible. Let's say v mu and goes on, right? And the Harishchandra theorem tells you that if in such filtration, this mu, whatever acting here, so Harishchandra will tell you that mu should be the dot product, whatever dot action we have seen, right? W dot lambda. So the mu should be of the form W dot lambda whenever you take the successive quotient by these maximal submodules. And this is a finite set. W dot lambda is, right? So W dot lambda is by definition, you're only taking small w dot lambda. So there are only w of lambda plus rho minus rho. That's the definition of this. So these are the possible irreducible quotients are possible. This is a finite set, right? And in each weight space, this m lambda itself has a finitely many weights of such weights. So that's why you get only finitely many highest weight vectors of such weights. Okay. So this somehow there are only finitely many mu's exist. So this process should stop due to this Harishchandra theorem, which I am supposed to do, but I couldn't. Yeah, excuse me for that. So the conclusion now is, so what you proved here. So you proved is, see, what is the use of this filtration? So if I have a filtration something like that, v1, let's say v here, let's say 0. If I have a filtration, then the claim is character of v such that, so I know, even forget about this thing. So even just take this filtration. So what this is telling, character of so v1 by v2, right? Which you know that its character of, so it's a fact that it's same thing as character of v1 minus character of v2. So I am writing this side, right? So if I know the successive quotients, if I know them, then I can get the character of the beginning module. So that's the use of the filtration. So the using the filtration there, what you can conclude here is character of m lambda is same thing as character of the quotients. The quotients are irreducible v mu's. So it is a character of v mu's, sum of the characters, where the mu is exactly w dot lambda. This is what this restriction is coming from the Harishchandra's theorem. There are only finitely many mu's are there. In particular, if mu is equal to identity, so it's only one time it will come. So this can come many times here. So it's here character of v mu may be occurring some finitely many times here. But the beauty is character of v lambda should occur only once, because the highest weight here m lambda has only one highest weight. So this is W not equals to 1. So this is like a triangular relation. If you analyze this, what you understand here, this implication telling you that. So this side I'm writing character of m lambda. And if you want to write a matrix form, see, I want to use character of m lambdas to get back the character of v lambda. So I have to somehow write this equation in terms of the other way I want it actually. Character of v lambda can be written as character of m's I want it. So for that purpose, you have to invert this. So to use the inversion, you use the system of equations here. So you are arranging this in a decreasing order. So maybe the next one is some orbit will come here, and that and this relation is telling you that character of m lambda, the this one will come. So this one will come only once. Only once is telling you that here one will come, and some star is here. This one, in this will not come because it's already gone. So if you apply this same result for the second highest weight vector, namely w dot lambda, then this one should come only once, and then rest I don't know. Similarly, what you are getting is, so it's an upper triangular matrix with diagonals are 1. Because this is a finite set, this orbit is finite set. So how many are here? Here this is a w dot. What is the cardinality of this size? So that is the size here you are getting, w dot. So you can invert this matrix. That's the beauty. When you invert this integer, so this is an integer entries. They're all integer, non-negative, in fact positive, non-negative. But you invert it, what you get is character of v lambda, the first equation I'm writing. It is again a m one time. Okay. Plus other, so although this is a non-negative integer here, so that you may get integers there. So the c mu's maybe or d mu's may be integers here. Then character of some m mu, where m mu's are w dot. It couldn't be 0 also. So this is what you are getting. Character of v lambda is sum of the characters of Varma. And once you use this, I know the character of Varma modules. The character of Varma modules are e power lambda by some product of 1 minus e power minus alpha, right? And then plus summation c mu, here w not equals to identity. So e character of m w dot lambda, so I'm writing as e power w dot lambda. By the same thing is there, so the same thing I'll move to everywhere it is same, so same thing I'll move to this side. It's a product of this. So I'll move everything here. What I'm going to get is this information. So it's a character of mu is e power, so w dot w not equals to identity. Yeah, I think so. I'm here. From this information, so the conclusion should follow. So what is the conclusion now? You observe the left hand side. Left hand side is this bit is while group invariant. So if you apply while group element here, this will be invariant. But this is not while group. I can't act on 1. So what you do, 1 is 1 only. So what you do, you take out so I'm just rewriting this bit. This bit has e power. So I'm taking out e power minus alpha by 2 out. So 1 will become, so e power alpha by 2 minus alpha by 2. So I'm just 1. So I just take out this. So the product of alpha greater than 0. Okay. So I'm just writing 1 minus e power minus alpha as e power minus alpha by 2 times. This is what I'm writing. Why I wrote this? This is actually this product of alphas. So there's a rho. Rho, you know that it's omega 1 plus omega n. But another description for this is half sum of positive roots. So whatever you are seeing here, this will be exactly equals to e power minus rho. So now you push that to that other side. So what you're going to get is product of alpha positive e power alpha by 2 minus e power minus alpha by 2 character of v lambda. If you put the other side, e power lambda plus rho is there, plus some while group not equal to identity. And do you remember w dot lambda definition? It's a w of lambda plus rho minus rho. I'm multiplying with e power rho now. So this is exactly e power w lambda plus rho is. Here there is no dot action here. Usually here. Now this is exactly what you are seeing in the numerator of the while character form. Okay, so the only thing, the denominator here, this denominator, no, by the way, there are CMUs are there, so they are still there. So the CMUs, I think I have to replace. So I don't know, it could be 0 separate. I don't know about CMUs. How do you control the CMUs? By looking the left hand side, this is a symmetric polynomial. Now you apply W to this while group element. So for example, apply W inverse to this. So if you apply W inverse, right hand side, what you are getting. So this side, left hand side, this is symmetric. If you apply W, those positive roots which are going to positive gives the same thing. Because W alpha here will come, there is another W alpha will come. So that's also gives a contribution. But once W alpha is negative, then this swaps the sign. So this is going the other way. Those roots are, so they give a negative sign here. So minus 1 power length of W will come if you act with W here. So maybe W inverse if you act, that's the same length, W inverse and W. Which positive roots go to negative under W is same thing as under W inverse, those negative goes to positive. So if you see right hand side, if you apply W inverse, then this coefficient of e power lambda plus rho should not change, right? So the coefficient of e power lambda plus rho is 1 here. And if you apply W inverse, the coefficient is something else you are getting, right? So being this side also symmetric up to sign will tell you that the C muse has to be 1, maybe up to this sign. So that's why this is a C muse. You can replace it with just by seeing the it should be symmetric with W action. This coefficient is only 1. This coefficient is only 1, which tell you that this coefficient also should be 1 if it is symmetric, if you act with W inverse. But left hand side is not exactly symmetric. There's a length is coming, so that should match. So that's why you're getting this. And this is exactly there in the numerator of the while character formula. And the denominator, if you want to get it, what you are getting is this one, whatever you are seeing here. So what is the character now? Character of V lambda is exactly you're getting minus 1 to the power of length of W e power W of lambda plus rho by some product of alpha positive e power alpha by 2 minus e power minus alpha by 2. This is true for any lambda dominant integral weight. In particular, this should be true for every zeroth weight also. 0 is the dominant integral weight. If I apply for 0, so if you want this equation, if you want the identity for this, you have to put lambda 0. Once you put lambda 0, it is only W rho is coming. So the lambda is 0 is telling you that you can replace this with wherever lambda is there, you keep it. So these two are same. The denominators are same. Okay. So although this formula involves the while groups, which involves this alternate sum and denominator like this. Yeah, please.
Sir, omega dot rho.
Yeah.
So then denominator is omega dot rho.
Omega dot rho. Omega of. Thank you. So I'm putting W is it is there is no dot now. It is dot is already here taken care. This is just a usual W of lambda plus rho. Okay, so W of rho lambda is 0 is just W. So although character is this, using while character the formula, there are many results are proved just using this. If some results are there, the questions are asked for V lambda, for example, because character is enough to determine the representation. So using while character formula, although this looks many things alternate signs involving, but it's very useful in proving some results about V lambda. Okay, so with this, I will stop. Thank you.
Any questions? Yeah, Sachin, please carry on.
Yeah. So, please, if you have any questions. In case not, let us thank Professor Ravinder for his nice set of lectures. It was great to have him here. I just needed a one phone call to kind of his acceptance for the lectures. And I'm I as an organizer along with Amit are very thankful to him. So we will again see him in the tutorials. Yeah, so thank you again.
Yeah,
so
thank you.
Just a couple of things. Yeah, so I have shared the feedback form. Please fill it up. Yeah, this gives a boost to all the lecturers who are preparing, as well as remember that if you are not attending the tutorial, then next week we are going to start our lectures at 11, and not before that.
So yeah, so can I stop recording, sir?
Yes.
Okay.
Thank you.